All right, so today I wanted to tell you how to finally solve numerically the implicit integrator rules. The one thing I've been wondering. But before we get there, I wanted to talk a little bit about the potential function, this e of x, which I always just take for granted, right? That's the function that for a given state x gives me the entire potential. And it's also important because it also tells us what our force is, right? If you have the potential, then the forces are usually written just as f. It's also a function of the positions, and that's just the minus gradient of the potential. And all conservative forces can be expressed in terms of the potential. And that's what we are focusing on right now, conservative forces. Okay, so let me talk a little bit specifically about what this E function is, okay? And let's consider, probably the best way is to explain using an example of a mass spring system. This will also let me give some examples of momenta conservation, because that's also want to tell you what integrators conserve momenta and what does that exactly mean. Okay, but first let's talk about how do you model a mass spring system using a potential. So what means a mass spring system? That means that you have a bunch of particles, particle P1, then you have particle P2, then you have particle P3, particle P4, particle P5, maybe somewhere around here with particle P6. And they can be connected with, I just draw it as edges, but you can imagine that those are springs. And there can be arbitrary connections between them. It could be something like a mesh, like a planar graph, but it doesn't have to be. That could be just like one spring connecting it like this. There could also be springs connecting it like across. So this would be connecting P2 and P5. So the connections are completely arbitrary. Now this piece, now let's assume we are in 3 dimensions, right? So each of the p's has x, y, and z coordinates. So this entire state vector, all of the positions of all the particles will be p1x, p1y, p1, oops, come on, well, p1z, then will be the second particle, and again x, p2y, p2z, and so on up to, let's say we have m particles. So this will be PMX, PMY, and PMZ. Okay, so all together we have 3m dimensions when m is the number of particles, right? Nothing too special. That's what we talked about before. But what I want to tell you now is how do you construct the potential corresponding to the mass spring system. So the first thing we need to figure out what is the potential for one spring. One spring. So one spring means that it has 2 endpoints, A and B. The spring also has some rest length R. And when the spring is at the rest length, it should be 0, the potential, right? What we started with the very first lecture was the 1D example of a spring, but when we are in 2D or even 3D, the Hooke's law gets a little bit more complicated, but that's what the potential, that's the basic potential for a spring that's still given by Hooke's law, except that now it's slightly more complicated because I have to compute the current length of the spring, okay? So that tells me that the potential for these 2 points, A and B, or particles, A and B, or nodes, according to Hooke's law, will be k half of a minus b minus r, the whole thing squared. Okay, where this k is stiffness of the spring, that's a parameter. The a and b, those are just the 3D vectors, so this is the norm. So this thing is the current length of the spring. And this R here, as I said before, that's the rest length of the spring. Okay, so what this does, it compares the current length of the spring to the rest length. So after I take the norm, this becomes a scalar. I subtract another scalar, so this is just a scalar. I square it, and I multiply by k half. Okay, that's just a scaling part. So this of course, this a minus b, that means Euclidean norm. So that actually means the square root of the a minus b squared, okay, so standard Euclidean distance function. And this is the standard Hooke's law model for a spring. Okay. The one thing that's important that this already is nonlinear, and it's kind of tricky exactly because of this square root there. Okay. So this Hooke's law becomes trivial only in 1D, because in 1D this norm you can basically you don't have to do it. Measuring the length in 1D is easy. Okay. Also becomes much easier if this r is 0, if the rest length happened to be 0. Okay, because if this is 0, then this reduces obviously to just the norm squared of a minus b, right? And that's just a quadratic function of a and b. But in general, the rest length should be non-zero, right? Because the spring has some non-zero length it wants to return to. So either when it's compressed below r, then it wants to expand. When it's extended beyond r, then it wants to shrink back. So that's what the rest length does. There is a variation on it, which I call the STVK spring, because sometimes you don't like this square root there, and sometimes you can do an alternative model, which would just square it in here. Okay, so a minus b squared minus r squared, and the whole thing squared again. Okay, so the STVK stands for Sandvenon-Kirchhoff material. We'll talk about it more in finite elements. But here it's just like a convenient variation on the Hooke's spring model. And what do you think is the advantage of this over this? Exactly, yes. You don't have any square root there. So actually this energy is a quartic polynomial, fourth order polynomial, okay? And that actually has some advantages which can be exploited numerically. All right, so this was for a single spring, okay? When we have a mass spring system, then we need to put it all together. So the potential of the entire mass springs system, this will be the E of x, when x is the vector stacking all the coordinates of all the particles. And one way I can write it, there's many ways, it's mostly a matter of notation. I can say that S goes from some set of springs, so that will be indexing all of the springs, okay? Then every spring has its own stiffness, so it will be the Ks will be stiffness of spring S. And then I need some notational things saying that I will extract particle number AS and compare it to particle BS. I can measure the distance. Let's do the Hooke's model. Minus RS, so that's the rest length of spring number S. And what this AS and BS means, that means the endpoint indices. So it's just a matter of some fairly simple data structures. So for example, in this example I drew here, I would have a set of springs that would be like 1 and 2, right? So that means that A of 1 would be 1 and B of 1 would be 2, right? Then I have another spring 2, 3, that would be this guy here. So the first one was 1, 2. Then there is the 2, 3. So that means that A 2, the 2 meaning here second spring, right? That would be 2, and the B of 2 would be 3. Okay, I guess you got the idea by now. Let me do one more example to drive it home. So then you have 1, 3 spring, right? So this is spring number 1, spring number 2, spring number 3. So that means that A of 3 would be 1, and B of 3 would be 2. Okay, you got it, right? It's just a matter of some simple arrays and basic data structures to organize all your springs in memory. And once you have this, then it becomes easy for any given x, and it becomes easy to compute this potential. Is that kind of obvious to you? Yeah, Brian?
Numbers is the physical location x, y, z of the point. Is that right?
What numbers is the physical?
A1 equals 1, B1 equals 2, for example?
Oh,
that
no.
1 and 2 equal the physical point?
No, so this A1 is just indices, okay? So what this A does, so the A takes index of the spring, okay, and returns the index of the endpoint of the spring. So A would be for the first endpoint, B would be for the second endpoint.
But that index stores the location.
The index does not store the location. The index indexes into here. and that's where the location is. Yeah. So like in a yeah, that's a great question. In a simulator, these things would be, I don't know, minus 16.5376, right? Those would be some like scalar values wherever the system happens to be. Okay, so yeah, those are the locations in this X, and those are just integers. Okay, indexing into that. Ankur? Yes, you're right. Thank you. So good points. Thanks. Okay, so this is kind of similar to like a mesh data structure, right? It's kind of same idea, except that this is used for simulation and not for rendering. It's kind of like when you have in graphics, when you have vertices connected with triangles together, and then you render it, right? Here it can be connected arbitrarily because the springs you don't even have to display, by the way. You can for debugging purposes, but you don't have to. All right, so if we just do a potential like this and we model some mass spring system, and that's your choice, how do you connect those springs? That requires some creativity. So this thing, if you start simulating it, now you can start simulating it, right? Because now we have a potential. We can also throw in gravity in the potential if you want to. We don't have to. You can give it some initial conditions. So you can give it some initial kick, some initial velocities, and some initial positions, right? So this is just the vector of positions, but you know we also have the vector of velocities. You can set it to 0, except that then it won't be moving unless there is gravity. So you can set it to something more interesting, so it's moving right off the bat. And then you can run any of the integrators we were talking about before, and it will do some simulation, right? And if you just do it like we said here, and give it some non-zero initial velocities, then this mass spring system is going to fly away. Because there's nothing holding it in place, right? It's like a free object floating in space if you don't have gravity. If you turn on gravity, it will just start falling indefinitely down and never stop if you use the standard linear gravity model. So what you typically want to do is to give it some constraints. And the easiest case of constraints are position or attachment constraints. And that's just a way of saying, a formal way of saying that you want to pin it down somewhere, okay? If you don't want your thing to fly away, if you don't want this to fly away, then the simplest thing you can do is to say that some of these guys are going to be fixed. For example, I can say P1 will be at this given location in space, and I prescribe what that location is in terms of x, y, and z coordinates, and then I say that's not going to change ever, okay? That's going to be a constant. So I can do this, and let's think about it. What does it mean? So that means constrain or fix some particles. Okay. So what does that mean? So if I fix, let's say we fix P1, okay? So in that case, what that means, and that's important to realize, is that we have removed the corresponding degrees of freedom from the x vector. Okay. If we now say that P1x, Pyy, and Pyz is fixed, then all the degrees of freedom, there is only now 3m minus 1, or 3m minus 3, if you will, degrees of freedom. Okay. So that means you remove its degrees of freedom from x. Okay. And correspondingly, you remove them also from velocities. Because if it's really pinned down, then it doesn't have any velocities. So those will be no longer simulated degrees of freedom, but you know what's important? The important thing is that in the potential, they still stay there. Okay, so let's take a look at it like this. If I have one spring, one spring, and one of its points is fixed, okay, let me still call it again A, and one is free, that will be B. So then I still need to account for the potential of all these springs, right? Even if this P1 guy is held fixed in place using, let's like imagine it's like glued to some wall, right? And you can physically also interpret it that there is always just the right amount of contact forces, which cancels all the other forces acting on the particle so it doesn't go anywhere. Okay, that's one physical interpretation you then attach to the position constraint if you want. But the important thing is that even though this is fixed, this spring still needs to be accounted for, right? Because when this is going to be moving, these springs will be stretching. So this actually, the potential of all these springs still stays there. Okay. The difference is that if I write down the potential, if A is fixed, the potential will be only a function of B because A is now constant. Okay. So the potential becomes only a function of B. You still have the stiffness and everything else stays the same. The only thing that changes is that A is no longer an argument. It appears here, but appears here as a constant. Okay, constant you give it. And that's the easiest way how you can achieve some interesting simulations, because then you can pin it at a point. You can give the whole system some initial velocity. So for example, in this system, if I pin this like this, and I give these points some initial velocities moving somewhere, then this thing will start spinning around this point, because this point cannot go anywhere. There are still springs which account for the energy of these, which basically does not allow these points P2, P3 to fly arbitrarily far away from P1. Okay? So that's kind of simple, but I just wanted to explain that. By the way, there is nothing preventing you from fixing both endpoints of a spring. Okay? I could easily say, hey, I want to fix P2 as well. I can totally do that, right? Now, in that case, the spring P1, P2 becomes a little bit funny because it doesn't have any degrees of freedom. So in the potential, it just becomes a constant. And constant in the potential is kind of moot, because when you compute the forces, the constant kind of goes away, right? It's kind of like in the gravity potential. It's an arbitrary where we actually put the zero, right? Because that kind of doesn't matter. What matters is the forces. But if you want to do it right, you can still account for whatever potential that constant spring would have. Okay, so if both are constant, then it's just a constant offset of the potential energy. All right, so I think this is all easy and clear, right? Ankur?
So if we keep both A, if we give some constant quantity both A and B, then the potential energy of system will never be conserved, right? So that's why you're saying that it will keep on moving to whatever direction it will, like it will never net down to zero, right? Is that what you mean?
That's right, yes. Unless actually you happen to constrain it such that this is exactly at the rest line, then it would be at zero. That's right, yes. Oh, by the way, you can do other fun things too. You can kind of say that this is constant, but you can say that this is actually changing in time kinematically. And that's what's done a lot in physics-based animation, because that's one way how an animator can interface with the simulation. Okay, so here I can assume, let's look at these two guys, P1 and P2, right? And let's say that I make them fixed. But that doesn't mean that they have to be at the same position all the time, okay? I'm still simulating in time, and what I can do, for every time step, I can change the value of this constant, okay? So that means that I kinematically prescribe some trajectory for these particles, okay? And that's a really good way how an artist can interface with the simulation. That's, I guess, the most basic way an artist can interface with the simulation, because what an artist can do, she can draw some spline curve, right? And say that these 2 points, or 2 spline curves, or whatever curves, could be linear curves too, right? And say that these points move along those curves. So that's essentially keyframing, okay? You can keyframe the trajectories of some of the points, and then have physics to resolve the remaining points, okay? So it's kind of a nice thing, because you can combine keyframing with physics. So if you want to do something, for example, like a curtain kind of sim. So I have some piece of cloth or something like this, right? Let's say that it's constrained here. These 2 endpoints are pinned, and maybe the artist wants to do some animation that I like shake the curtain, so it goes along some trajectories like this. So this is a way how you can do this. Okay. Now there is a word of caution here. If you are changing the potential, then you are changing the Hamiltonian too. And the things such as conservation of energy do not apply anymore. Because the conservation of energy assumes that the Hamiltonian is constant in time. Now, if you give it keyframe animation for some of the vertices, your Hamiltonian is no longer constant in time, so you cannot expect energy to be conserved, right? Which kind of makes sense, because if you say, hey, these guys are kinematically moved, you can interpret it that there is some kind of hand of God or something moving these particles along, right? And clearly, if you move some of the particles along, if you move some of the particles kinematically, you might inject or decrease the total energy of the system. Okay, so the energy conservation only applies if the Hamiltonian is constant. Ankur?
Something like we will not like manipulate them using the keyframing, but we apply some kind of force, but we construct the force in such a way that it only affects those control points. And then in that way we can keep them. Well, it'd be better. I mean, it'd be easier to keep the energy conserved in that case.
Yeah, right. That's another way you can look at it. It would probably end up being equivalence, just a different formulation of this, by saying that instead of putting this constraint here, you can say that there is some external force acting just on these particles, right? And you can totally do this. It's kind of similar to particle systems, which is sometimes also used in animation. And you can then invent essentially your potential acting just on these particles. Now the tricky thing being, if that potential is also changing in time, that you also don't conserve the energy. But that's fine, right? Because that's what you want. If you actually have some external forces acting on it, you actually want them to inject energy in the system. So that's fine. Just so you know what is going on and what you should expect from the simulation. Yep, very good point. All right, so before we get into the numerical solutions of implicit integrators, I just wanted to use this setup to talk a little bit about what does it mean to conserve momentum. So momentum conservation. We talked about this in the continuous case, in the exact solution thing, right? Remember how we talked about first integrals. Some first integrals corresponded to linear momenta, some to angular momenta. So let me actually quickly recap that. So what we had before was that if E is translation invariant, then there exists a linear momentum or linear momenta are conserved. And I'm saying it in this fuzzy way because there can be one, there can be two, there can be three, okay, if we are in 3 dimensions, depending how exactly translation invariant it is. It can be translation with respect to one axis, it can be translation invariant with respect to all possible axes, okay? Then we also had that if it's rotation invariant, then corresponding angular momenta are conserved. And this both means in the exact solution, in the exact continuous solution. So actually, let me do a few examples using these mass spring systems just to make sure, just to kind of illustrate the different possibilities of what all can be conserved, okay? So the first example will be completely free 3D mass spring system. So any number of particles, any number of springs, okay, it's all in 3 dimensions. So how many, let me ask this way, how many conserved quantities are there going to be? So for just let me remind you, the linear momenta, they were linear first integrals. First integral is a function on the phase space, like linear momenta is a linear function. Angular momentum is a quadratic function, which is multiplying the positions and velocities together, along with these funny matrices corresponding to cross products. Okay, but and those are functions, and you can have a certain number of these functions. You can have up to 3 linear momenta and up to 3 angular momentum if you are in 3D. Okay, so in this case, when you have a completely unconstrained, so no position constraints, completely free 3D mass spring system, how many momenta are conserved? It's kind of easy, I guess. So I assume conservative forces, right? So one of the first integrals that's always conserved is the energy. If I assume that the Hamiltonian is not changing, so if I'm not doing this kinematic control. So how many momenta would be conserved? And momentum is a function, right? And there is how many functions do I have that are conserved throughout any motion of a free mass spring system. I thought it was gonna be trivial. It is trivial. Maybe you're looking for some trick, but there isn't any.
Is it both linear and angular? If it's free, there's no forces on it, so it would always be conserved.
Yeah. All linear momenta and all angular momenta are conserved. There is a maximum of 3 linear and 3 angular because we are in 3D. So yes, in this case, when it's okay. So the way I guess how should you figure it out, right? What you need to figure out is what is the potential invariant to. Okay, so let's see if I can select and erase this because that's what I want to do. I guess not. I can do it like this. So imagine that these guys are no longer constrained. Okay, there's still my P1 and P2, but they are no longer constrained. Okay, so what the potential is symmetric to? It's symmetric, or what is it invariant against? Okay, so let me ask you this way: if I take all of the points and translate all of them by the same amount, will the potential change? It won't, right? Because if I just translate the whole thing, these might have been stretched or compressed, so there might have been some potential energy, right? But if I just translate the entire compound, the potential definitely is not going to change. And I can translate it along any axis. I can translate it x, y, and z axes, okay? From what we had before, that immediately implies that x, y, and z linear momenta are conserved. So there are 3 functions of linear momenta which are conserved. Okay. Now, a slightly trickier case. What about the rotation? So if I again take this entire compound, so this entire x, right, all the positions of all these particles, and I rotate the entire thing. Okay. So this time I take this and I, about some point, whatever point I choose, and I just rotate this whole thing. Will the energy change? Certainly won't, right? Because rotation preserves distances between points, right? And hey, guess what? I have 3 axes in which I can rotate about in 3D, and a rotation about all of them will conserve the potential, okay? So again, I have 3 angle momenta which will be conserved in this completely unconstrained case, okay? So in this case, I have the maximum conserved quantities, so 3 linear momenta plus 3 angular momenta are conserved. And the Hamiltonian, that's right. But let me just talk about the momenta. Because what I want to then get to is that some of the numerical integrators actually will conserve the momenta as well, and some of them won't. So first let's illustrate this a little bit. What does it actually mean in the continuous case? Okay, so now we are still talking about the continuous case. So actually, example number 2, what if I fix one of the particles? So I fix one particle. Again, 3D mass spring system, right? Now I fixed one of the particles, let's say P1. What momenta will be conserved then? And to answer that question, you have to think, what is the potential going to be invariant against? If I say that one of these p's is no longer a degree of freedom of my simulation, but instead it's a constant, okay? So it's this case that one of the guys becomes a constant. So what happens to the momentum, to the momenta that are conserved?
Linear momentum would not be conserved.
That's right. So linear moment, so no, not conserved. Yep.
And you could rotate it about that point specifically on any axis and still maintain. So I don't know if you couldn't choose a point to rotate it about unless it was that point in this example.
Yeah, Brian, that's a great insight. Yes, before you could rotate it about any point, right? Now you have to be careful about rotating it just about the point that is fixed. That's right. But if you rotate it about that point, then you still have three angular momenta that are conserved, right? And that becomes a little bit subtle because there is an interplay between translation and rotation, okay? I don't want to get too deep into this because if we dig deeper into it, we get to SE3, the special Euclidean group in 3 dimensions, and subgroups of SE3, and that's a little bit more of a group theory than I wanted to go into, but that would be a way to formalize this thing, rotating just about a point, okay? Nevertheless, you can still, the question I posed here is, what first integrals can you find? And the answer is you can find 3 angular momenta, which will be axes passing through the point I happen to fix. Okay, and then they are conserved. So in this case, we had a total of 6, right? We can find 6 first integrals which are not the Hamiltonian. In this case, we can find 3. Okay, let's do 2 more fun examples. Let's do something more complicated. Let's say you have like an elastic cube, which has like bunch of particles, kind of thousands of particles. Okay, so particles all over the place. There are some springs connecting it in whatever way you would like, and then let's say that there is some axis. So all these points are on a single axis. Okay. So that's a perfectly straight line. And all these points are position constrained to stay on that line. Okay? So all these guys cannot go anywhere. The rest of them, they can go wherever they want. Those are free. These are fixed. So what happens to my momenta? So Abhishek, yep.
Linear won't be conserved.
That's right, yeah. None? That's right. So you have just one angular momentum, and that needs to be the axis. Okay? So angular momentum about precisely this axis will be conserved, right? Because again, if I rotate the entire thing about this, all the springs will have the same length, so the potential will be the same. That gives rise to exactly one angular momentum that will be conserved. So now we are down to just a single momentum that's conserved. Okay?
Question.
Yep.
Are those points fixed specifically on that spot on the line, or could it translate across the line?
That's a perfect question. That was actually my example number 4. So here I meant that they are actually frozen on the line, specifically where they are. Just like we had here, just replace it with a constant, no discussion. Okay. But what you brought up is an excellent thing. So now we can, let's say, same as 3. But now, particles on the axis can slide. Okay, so this would be a little bit more complicated, right? You would have to like parameterize it in the right coordinate system so you can write the sliding constraint. By the way you could do it, the A and B here, they have X, Y, and Z, right? And you can constrain it partially. You can constrain only the X and Y, for example, right? So that's what you could do here. You could say, hey, this is, by the way, my Z axis, okay? And I only constrain the X and Y of these points. So now these guys are free to slide on this axis, right? You can imagine you have like a cube and that's kind of pinned on it, but then it can move back and forth along that axis, okay? So what happens to momenta in that case? Exactly, you got it. Perfect. That's what I. So there will be one linear momentum, and that will be again exactly the axis, right? And the angular momentum, of course, that still stays as before. So now actually I have 2 momenta that are conserved. All right. So there are all these cases out there, and you could actually come up with a more sophisticated cases, right? You could also have like a special, like a helix kind of constraint that would be some more non-trivial subgroup of SE3, but I said let's not go there. What I want to explain here is what does it mean that a numerical integrator conserves momenta? okay? Which is a little bit tricky thing to think about because even the exact solution, and here all this stuff was about the exact solution, okay? Just pure math. No funny numerical business, no floating point errors or anything like this, just pure math, okay? But even in this case, there are all these cases, right? So how do we reconcile this with the properties of numerical integrators? We do this definition, and basically I will say that a numerical integrator is momentum conserving. So that's just a terminology kind of thing, okay? If it conserves the same momentum as the exact, meaning continuous, solution. Okay? And I need this kind of like a legal kind of wording because I don't know a priori what the potential is invariant to. Okay? In these cases, it was actually kind of easy to figure out. But sometimes you are just given a potential and you actually don't know what is it invariant to, right? And the numerical integrator most definitely does not have this information, okay? The numerical integrator is just a piece of code. And the piece of code, all it does, all it gets to do is it gets to evaluate the gradient of the potential at certain points. That's all it can do. And it should not do too many, right? Because all of these evaluations are expensive. It gets to evaluate the forces at certain points, right? Like if you have the RK4, it like samples like 4 points or something like this, and then tries to figure out a step based on that. The integrator does not try to detect these invariance properties, okay? That's an important subtlety. So the numerical integrator needs to be designed in a way, so if the numerical integrator is to be called momentum conserving, so it's kind of a terminology kind of thing, just to explain what does it mean. If it's momentum conserving, it cannot mean that it conserves all the momenta, right? Because already the exact solution doesn't conserve all the moments. It would be ridiculous to want that. So it means that the numerical integrator is a piece of code, an algorithm that needs to be designed in such a way that if the potential happens to have these invariance properties, then the numerical integrator does not mess that up. Okay, it preserves the same first integral the exact solution would. Okay, so that's what this means. And before we talked, I won't go into proofs, I don't want to spend forever on this, but we talked about palette of numerical integrators, right? We just put the shortcuts here. We talked about forward Euler, we talked about backward Euler, then we talked about symplectic Euler, implicit midpoint, and implicit Newmark, two closely related advanced integrators. So I won't go into the proofs, but I will just tell you what momentum conservation properties they have, okay? So it turns out that all of these are conserving linear momenta, okay? All are linear momentum conserving. And it's not too hard to prove. If you want, you can try to prove that. And again, this means that if the potential has the corresponding translation invariant, then the numerical integrator will preserve the corresponding linear momenta, okay? So now it's no longer a statement about the exact solution, but a statement about the approximation produced by the numerical integrator, okay? And that's kind of important. It's similar to energy conservation, right? The numerical integrator always makes an error. It's always just an approximation, okay? And it's a bigger error than just the rounding errors, which are happening in the computer just because you have a limited number of digits. It's a bigger error. It's an error due to the fact that you are taking a finite time step instead of infinitely small time step, okay? So numerical integrators, no matter how fancy they are, except for these special analytical integrable cases, which are very rare, they always make an error, okay? But these things are great because they tell you, hey, they actually don't happen to make an error in certain aspects of the solution, okay? And here these aspects are the linear momenta. Now, angular momentum conservation is much trickier, it turns out, and that's exactly because linear momenta are linear functions on the phase space. Okay, linear means easy in mathematics. Angular momenta are quadratic functions, and quadratic means slightly trickier. So not all of these integrators preserve angular momenta. It turns out that the only ones that preserve angular momenta are preserving. So the only ones that do that is from this class is the symplectic Euler and implicit midpoint. The other ones do not conserve angular momenta. And you can kind of clearly see it if you run this simulation. This one is a good test, like a cube fixed to an axis, cannot slide, but it can spin around the axis. If you try to integrate it with forward Euler, what you can see is that this will keep speeding up, even though that's impossible. And with backward Euler, this will be slowing down. And that means that the angular velocity about this axis is not constant, even though it should have been, because I don't have any gravity, I don't have any dissipation. Okay, it's just an error of the integrator. If you run the same simulation with symplectic Euler or implicit midpoint, this cube will spin forever because the angular momentum about this axis is conserved. So that's why these integrators are superior. The implicit Newmark is a funny case. It's also because it's not symplectic and angular momentum preserving in the standard sense, but there is a different sense of symplecticity, and there's actually a different sense of angular momentum the implicit Newmark preserves. Okay, so the implicit Newmark is almost as good as implicit midpoint if you look at it a little bit differently. Actually, I think the precise statement is that implicit Newmark happens to preserve angular momenta if they are evaluated at the midpoint of the interval. Okay, if you have your time step from I don't know, xk to xk plus 1, okay? Normally, you would evaluate the momenta here, right, at those time steps. It turns out that the Newmark would actually preserve angular momentum if you evaluate it right in the middle. So this is a little bit funny, but it kind of explains that implicit Newmark is also a high-quality integrator. And lots of people like using it in physics-based animation, even though there is no guarantee of stability, okay? None of these have guarantee of stability. Backward Euler seems to be empirically perfectly stable, okay? We have a little bit of proof with Dimitar in some very simple case that it actually is stable, backward Euler, and it's believed it's stable for all reasonable potentials, but as far as I know, there is no proof. That's an open problem as far as I know. But then the problem that backward Euler does not conserve angular momentum and does not conserve energy. So kind of there is no perfect solution out there. All right. So if you want to solve these, if you want to actually try this, implement these integrators, if you want to try backward Euler, implicit midpoint, or implicit Newmark, they are all implicit integrators. Okay. So let's finally look into how to solving, and let's start with solving implicit Euler or backward Euler. That's the same thing, okay? So implicit Euler has these update rules, unless you had some more questions on this. I'm trying to get it all covered. Okay, great. So let's talk about how to actually solve this numerically so you can actually implement it on a computer and play with some fun simulations. So let me just write down the update rules of backward Euler plus h forces at xn plus 1, right? You know that the tricky thing is this n plus 1, right? And that's what makes it an implicit integrator. Let me call these guys 1 and 2. There are two update rules, one for the positions, one for the velocities. And the question I would like to talk about now is how to actually solve this system of equations, okay? First of all, it would be easy if the forces were linear, because then it would be a system of linear equations, but that's usually not going to happen, right? Even for these simple mass spring systems, the forces are already non-linear in both the STVK case and the Hooke's law case, right? They would only be linear if all the rest lengths were 0, okay? But that's actually not a very interesting case, right? Because with rest length 0, you cannot do a cube like this, right? Or you could do a cube, but what the forces would do, it would shrink the cube to a single point. So that's not a very interesting case to look at. All right, so what shall we do here? I guess the first thing you can do, you can just feed it to some nonlinear solver. You can, like, if you have some MATLAB or Mathematica or even some libraries for C++, you can just directly hand over these equations to a nonlinear solver. And it will do an okay job depending on how good solver it is, okay? It will not do a perfect job at it for a reason I will explain just now. So how do we solve this? So first, let's turn this into one equation, okay? Because dealing with 2 is slightly annoying. So the first thing I will do is multiply the equation number 2 by h, okay? So that's, and put the hvn on the other side. So I'll get hvn plus 1 minus hvn equals h squared of fxn plus 1, okay? That's easy, right? And now, let's see. Right, now from the first equation, I can express what hvn plus 1 is, okay? So this term, okay? So from the first equation, I can write that hvn plus 1 actually is xn plus 1 minus xn, okay? I'm trying to solve the system of equations, so I get to massage it whatever I want, right? I want to get it into an easier form to solve, okay? So hvn plus 1 is this, so I can take this and plug it in here. All right, so if I do that, then I will get xn plus 1 minus xn minus hvn equals h squared of fxn plus 1, okay? And this is a little bit easier system of nonlinear equations to deal with. It's not a big difference, but this was a system of 2n equations, right? And this is a system of just n equations. So it's a little bit better. Now also notice that this minus xn minus hvn, that's what I know, okay? The setup here, as you know, is that xn and vn is given, h is given, the function f is given. That's a function you can call on any point you give it. What you don't know is the xn plus 1 and vn plus 1. Okay, here, and that's why I did it, we eliminated the vn plus 1, so now we need to solve only for xn plus 1, okay? But these guys, they are given, we already know them, okay? So what we can do is we can say, hey, let me introduce a notation, let me introduce a new parameter y, which will be xn plus h vn, okay? And if I do this, then I can write this as xn plus 1 minus y equals h squared of f of xn plus 1, okay? Because this y is a constant, I don't have to be writing this whole thing. I just say, let's call this y, okay? This y actually has a beautiful interpretation I'll get to in a second. First, let me simplify the notation even more. Instead of xn plus 1, I'll just write x. Okay? So I don't have to be writing the n plus 1 all the time. So here, again, the x, but the important thing is the x is the unknown. The x is, by the way, still the same thing as here. Those are the positions of all the particles. Okay, that's what I need to solve for. Okay, so now we need to solve for this. Now at least it doesn't look so messy as this stuff. Now we have only one equation, and the symbols are a little bit more easy to deal with. But let's talk about this y thing for a second, because the y thing is actually a beautiful thing that we got just by massaging the implicit Euler update rules. Do you know what this y thing is? The y thing is, this is actually exactly Newton's first law. Newton's first law says that if there are no forces acting on a moving object, then the moving object keeps moving on indefinitely with a constant velocity. Okay. Hey, and this is exactly what that is, right? At time in a discrete case, I have this position, this velocity, this h means that this velocity gets multiplied by a time h, so that's a position difference, right? So this means that if h is my time step, then if there were no forces acting on my system, the new positions would be exactly this y, okay? Now, of course, that's not very interesting physics-based system if there are no forces acting on it, because indeed, Newton's first law is kind of boring. It just keeps going with a constant velocity, okay? But that's this y, that's what this y is. That says where the positions would go if there were absolutely no forces acting on the system, okay? There is another way you can look at the y, because look what I can do. I can take the rule number 1, right? And this also applies for n minus 1, right? It applied in previous time step 2, right? So the rule number 1 for the previous time step was xn equals xn minus 1 plus hvn, right? That's the previous time step version of these rules. I just took one away from all the indices, okay? So this tells me that the hvn actually is nothing but xn minus 1, okay? And I can plug this into the y, right? If y was xn plus hvn, and now I know that hvn is actually xn minus 1, then this means that this is actually 2xn minus xn minus 1, right? And if I actually put it back in here, okay, this y thing can go right in there. So what do I get? I get, there's the xn plus 1, that is minus 2xn and plus xn minus 1, okay? And that whole thing equals h squared f of xn plus 1, all right? What I'm doing here, that's a different way how you can interpret this system of equations, okay? And maybe it helps if I actually divide by h squared here. Xn minus 1 divided by h squared equals f of xn plus 1. And does this look familiar to you? This. Yeah, except that nothing is squared, right? So kind of look at these coefficients here, right? Here is a coefficient of 1, here is a coefficient of minus 2, and here's another coefficient of 1, right? So those of you who do image processing, you must have seen this stencil. Correct. For second derivative. So this thing on the left-hand side, let me get rid of these guys. This thing on the left-hand side is just a central difference approximation of the second derivative of x at n, okay? So this whole thing is a central difference approximation of x dot dot at n, okay? What is x dot dot, the second derivative of n? Well, that's acceleration, right? So hey, this is nothing but Newton's second law. F equals m times a, okay? I made it easier by saying that the masses are identities, so this is just F equals a. Discretized using central differences. That's another way how you can look at this. Now you can forget about all this. This was just kind of giving you an interpretation of what this formula means, that this formula is not just some arbitrary piece of math, but it actually carries all this physical meaning to it. So now the rest of the lecture today will be about how do we actually solve this, okay? So we can forget what y was. Y is now just a constant, okay? Just like h is just a constant, okay? And now the question is, how the heck do we solve this? X minus y equals h squared f of x. Right, where this f can be potentially some complicated nonlinear function, okay? Any ideas how to solve this? So whenever you are dealing, so the only problem is this nonlinearity in the f, right? If the f was a linear function, you would just call a linear system solver, and that would do the job for you. Okay. So the first idea is to linearize f. If it's not linear, what you do, you just linearize. Okay. So linearizing f. So of course the f is a function of 3m to 3m. It's a function which takes all the positions of all the particles and outputs all the forces on all the particles, right? It's also the gradient of the potential. So the linearization, that's just a multivariate first order Taylor expansion. Okay, so I can approximate this function f at some point x0, okay? I always need to pick a point where I'm linearizing at. So if I pick this x0, then I can approximate it like this, plus the Jacobian of f at x0 multiplied with x minus x0. So this is a 3m by 3m matrix, the Jacobian. So, and this is a matrix vector product. Okay? So all that means is that I am at some point x0. I get to pick whatever x0 I want. And at this point, I can linearly approximate the function using the Jacobian. Okay? By the way, this Jacobian of f at x0 is nothing but the Hessian of the potential at the same point, of course. Okay? Correct, sir. Yes, negative Hessian of the potential. I always forget this, and then it doesn't work, surprisingly, if you forget the minus there. That's simply because the thing I always write, right? That the forces are just the negative gradient of the potential. So the Jacobian of the forces, that's what appears in this linearization, is just another derivative. So that means a second derivative. That means a Hessian of the potential. Okay. Just to be clear, we are on the same page. What Hessian means: if I have an arbitrary function h, then the Hessian of the function is a matrix of second derivatives. So it means I differentiate the function twice by x1, and then differentiated by x1 and xn. And here I differentiate by xn and x1. And at the end, I differentiate twice by xn. Now, you know from calculus that doesn't matter if you first differentiate by x1 and then by xn, or first by xn and then by x1, which means that the Hessian is a symmetric matrix, always. Okay? So once we have this linearization, and it just means computing another derivative of the potential, okay, so I will explain in some other lecture how to compute the derivatives of things like mass spring systems and then FEM potentials. But then once we have it linearized, we can just plug it in there, right? So what we can do is we can say x minus y equals h squared, and then we just do this f x0, or I should say approximately equal, right? Because this is what these tildes mean. It means approximately equal because it's not exactly, it's just an approximation. X minus x0, right? I can totally do this. And then what I can do, I can put this all, I can collect the terms with the x's. Okay, so I'll get x minus, what I will get? H squared, let me write it in terms of, whatever, the potential, the Jacobian is fine. I could also write it as Hessian, but that does not matter, with x. And that will be approximately equal h squared of f of x0, and this Jacobian of f at x0 applied to x0. Okay? So what this is, this thing on the left, you can write it simply as the identity matrix minus h squared, Jacobian of the forces at x0. So that's a matrix times x. And this thing on the right, that's just some right-hand side, okay? That's a constant, because the x0 I get to pick. That's a constant thing, okay? This matrix on the left is also constant because I can just evaluate this, and now I'm down to solving a system of linear equations. Okay, I can solve it. My solution is x. Okay, and after I have x, I will just simply say, hey, xn plus 1 is this x I have just solved for, and vn plus 1, well, vn plus 1 I compute from this update rule, right? So vn plus 1 is xn plus 1 minus xn divided by h. Xn plus 1 minus xn divided by h, okay? And I call it a day and move on to another time step. This method is the classical physics-based animation method due to Baraff and Witkin. I think 1997 or 8. The important thing to realize here that this is only an approximate solution. Okay, this xn plus 1 and vn plus 1, if you plug it back in here, it actually does not satisfy these equalities exactly. Why? Well, because I have these tildes here, right? Because this linearization is not exact. It's just an approximation, okay? Oh, you could be also asking what is a good x0, right? What x0 should I pick? An excellent choice is exactly this y. Or you can start at the previous time step at the xn and vn. That's also a possibility. So this is only an approximate solution of the backward-Euler update, okay? So only approximately with some error, okay? Depending on the time step, how big the error is going to be. You can actually kind of see that if the time step is going to 0, that this entire term, the ugly Jacobian term, goes to 0, and you just end up having here this identity matrix. So it actually becomes kind of more and more easy to solve the system of linear equations than with large time steps. Okay, and we'll talk some other day about how to solve the system of linear equations numerically. Okay, but that will be another discussion. So right now the problem is that we haven't solved it exactly. So actually, if you just do this method, it can still explode, even with backward-Euler. And the reason for these explosions is exactly this approximation here. Okay. So what we can do is to say, well, okay, how about we solve it more accurately? Okay. How about we actually try to solve these update rules as closely as we get, like up to numerical precision of the machine. So that is kind of easy to do, because all you need to do is to just iterate this entire process several times. Okay, maybe let me just illustrate it in 1D case. Okay, what we are doing is root finding. Okay, so let me maybe draw a better one like this. So let's say that this is my x0. Okay, what I'm doing here, or what Baraff and Witkin are doing, they are basically forming a linear approximation of this function. Okay, linear approximation means a line in this 1D case. This thing is my function h, and the task I have is I want to find the root. I want to find an x such that h of x is 0. So I'm looking for exactly this point where it crosses 0. Okay. What I've done here, the Baraff and Witkin method, is essentially one iteration of Newton's method, or also known as Newton-Raphson method, which forms this linear approximation. So you can kind of see if you are close to x0, it's a good approximation, right? But we go as far as we need to intersect the x-axis, okay? So then the solution, this x, that's what the solver gives you, that the x that solves this linear system, that's right here, okay? If this h is close to linear, then this x will be close to the root, but it generally doesn't have to be, okay? So the way you can fix this if you want a more accurate solution is to say, hey, this x is going to be my new x0, okay? So when I'm gonna go back up here and make another linear approximation right there. All right, that's another linear approximation. I solve another system of linear equations, and I get here. Okay, and as you can see, if I iterate this process, I very quickly converge to the right solution to the actual root. Okay, except for when I don't. Okay, and that's another point for discussion. But in the good case, if you're optimistic, then just repeating iteratively this process will get you there, okay? Now, one question you can have is how many iterations do I actually have to do? 5, 10, 1,000? And how do I detect if something went wrong, right? Because this thing does not always have to work, right? It's kind of easy to imagine an example where it doesn't work at all. If I have something like this, and the potentials, they don't have to be convex functions or anything like this. And the force is just as well, right? What happens if I start the Newton's method here, right? What if this is my x0, and here is the root I'm looking for? Do you know what happens? It won't. It will converge somewhere. It won't converge to the solution, right? This will probably converge here. Correct, yes. It will not give you a value that actually solves the system of nonlinear equations, unfortunately. It will get stuck in the local minimum, okay? And that's a problem because then we don't have the right solution, right? So how to answer both of these questions? How to first, if it works, how do we find out that we don't need to be iterating anymore? And how do we check whether it actually worked? So at least we can like print a warning to the user or something that it didn't quite work, right? So we can, that's by the way a good practice to at least check if you computed the right thing. And if you don't know how to compute the right thing, then at least please print a warning to the user that something probably went wrong. Well, so the way you can look at this is that if you are solving, so if you are solving this problem, x minus y should be equal to h squared of f of x, right? And the way we can track progress and check whether we found a good solution or whether we can stop iterating is by defining an error function, okay? E of x, which will be an error function which essentially measures how much we are violating this system of nonlinear equations. All right, so the easiest error function would be like this, right? Put this on one side, so this should ideally be 0. This is a vector thing, right? So that's what makes it a little bit tricky, because the solution is no good if you have all zeros and one that would be like really high, right? You need to drive all of the components of these vectors to 0. So that's why you need to put some metric, the easiest being the squared Euclidean metric, right? So that's what I did here. Sometimes this error function is also called a merit function in some optimization literature. Merit function, okay? And clearly what you want to do is you want to minimize the error function, right? You want to minimize this ex over x. That's a different way how you can formulate that problem, right? So you want to minimize this entire thing, okay? But there is a problem here, because if you look at what this merit function is, there's this ugly squaring thing, okay? And that's the easiest merit function. If you wanted to compute maximum or square root it would only get more complicated. So let's look at what happens with this squared error function. So for example, with the STVK springs, f was what order polynomial? The e was 4th order, right? Because we had powers of 4 appearing in the expressions. The f is a derivative, so the derivative takes 1 degree down. So the f is a 3rd order polynomial.
Are you talking about the example we did in class equation, or where did the 4?
Oh yeah, the 4 is this STVK thing, okay? Where did the 4 came from? The a and b, those are them. They are squared once. Here they are squared against, so that's 4. Okay. If I differentiate, 4 becomes 3, right? Because x to the power of 4 becomes f4 times x to the power of 3. So there are no more powers of 4, only powers of 3. Okay. Now, unfortunately, if I square it again, this 3 becomes 6. Okay. So in this case, the merit function becomes 6th order. Okay, and that's kind of a high order, because the higher order the polynomial, the more likely you are to have some local minima like this, which can make it not work, right? That you can get this. So the higher order, the more wobbly the polynomial is going to be. I'm not talking about a multivariate polynomial, right? Here I'm just drawing the single univariate polynomial for illustration, but this can have thousands of dimensions. So you can potentially have lots of local minima down there where the Newton's method can get stuck, okay? Now, fortunately, there is a better way of doing this, and that's also the main reason I just don't recommend feeding it to a nonlinear equation solver directly, because there is a better way how you can solve this, okay? If the forces are conservative, but that's what we are assuming, okay? So the better way is to do this, to formulate a function gx, which will look like this. It will be 1/2 of x minus y squared plus h squared e of x, okay? And do you see what happens? If I take the gradient of g at x, the gradient is going to be what? It's going to be x minus y, right? And here it's going to be minus h squared, the gradient of e, plus the gradient of e at x, okay? Or I can write this as x minus y minus, that's where I get confused because I always get this wrong, forces at x, okay? But hey, if I set this to 0, I have the same equation I started with. I have this equation, okay? Set this to 0, well, that's exactly what we have here, okay? So that means that this g function, the critical points of this g function are exactly equivalent to solutions of this, okay? And what is the advantage of doing this? Well, if we have the STVK springs, then the g function is what order? Only fourth. Because the e is fourth order, okay? This is just quadratic, so that hides under the 4. This is only second order, okay? So this g is only a fourth order polynomial, so less opportunities for these funny things. And the beautiful thing is that you get directly the potential there, okay? So this means that instead of solving the system of nonlinear equations or minimizing the merit function, what you can do is to be looking for critical points of the g function, okay? Now let's look at the g function. It's composed of 2 terms. This first term is obviously convex and quadratic, right? Because the y is fixed. Whatever y is, that doesn't matter right now. For whatever y, that is a convex quadratic function, okay? The potential functions, they don't have to be convex, but they are usually, and that's a very mathematically precise statement, they're kind of convex, okay? I will elaborate on that later, but for now, kind of trust me that it's sort of convex, okay? So this whole thing is sort of convex, okay? So that means it sort of looks like this, okay? The sort of means that actually there can be like a little bump down here, which makes it non-convex, but it turns out you don't have to worry about it too much, okay? So you can basically assume that this entire function g is convex, in which case looking for the critical points is equivalent to just minimization of gx, okay? So if you solve this minimization problem, you get a solution for here, right? Because if you have a local minimum, clearly the gradient is 0, clearly you have a solution of this, and if you solved it exactly, if you find exactly the minimum of that thing, then you have the exact solution to the backward Euler update rules, okay? You still need to, of course, this just gives you the x, you still need to compute the v's, but you do it in the same way as here, okay? And why do you want to minimize the g instead of minimizing this e? Because this is less nonlinear. Also a very precise mathematical statement, but you can make it precise by going to STVK and say, hey, this is just fourth order here. I probably want to be minimizing that rather than the 6th order thing here, okay? Less opportunities for local minima. You are raising things to lower powers, so also numerically the things won't be as crazy, right? Like imagine like number like 100 raised to the power of 6, that's going to be a lot, right? You would rather be raising it to the power of 4. So it turns out that this works much better if you hand it over to a solver that minimizes an arbitrary nonlinear function, which is also kind of convex, okay? So that's, in my experience, the best way you can be solving all these implicit update rules, by running a minimization solver on this G function. Okay, and we will do some next lectures which will talk about how to minimize this. This is again Newton's method. Okay, this time Newton method for minimization, optimization, which is a little bit different than Newton's method for root finding, as we talked about here. It's kind of similar, but it has some subtle differences. So we talk about that. We'll also talk about how to solve the linear systems. And because I still have a couple of minutes, I will give you a kind of fun interpretation of what it means to minimize this gx. I guess that's a general kind of advice. Whenever you see some formula, try to think about it. What does it actually mean intuitively? Okay, and in this case, it's kind of cool. Minimizing this thing, this is a sum of two terms. Okay, this one is perfectly convex. This one is kind of convex. Or we can even say that you can pick some easier potentials which are convex. For some of the tests we do, we sometimes just pick convex. So we can assume this E is exactly convex. Okay? So what the minimizer of G of X is going to be, it has to do a trade-off between these two things, right? It cannot minimize just this one thing, because then this one could go out of the window. It cannot minimize just this thing, because then this thing could be huge. So what it's actually doing, it is striking a balance between the two terms. It's looking for an x such that when I plug it in here and I plug it in there and sum the whole thing, I will get the lowest possible number. Okay? What is the first term? The first term says in English that x should be close to y. Okay? That's what it does, right? This first term will be minimized exactly when x is y, right? What was y? Y was Newton's first law. Y was saying where the system would go if there were no forces acting on it, okay? That's what the first term says. The second term says, hey, by the way, there are forces acting on it, okay? In that case, I need to make both of them happy, okay? And that's what this minimization means. You can also look at it that this is like an inertial term or inertial force term, if you will. And this can be the elastic energy term for your mass springs, plus gravity, plus whatever other potentials you want to throw in there, right? If you are a technical director of simulation at Pixar, then your job essentially is, to a large extent, inventing what potentials you can throw in there so the simulation does whatever the director wanted. Okay, but doesn't matter as long as this optimization is concerned. You are just minimizing this, and we'll talk next time about how exactly to minimize that. Okay. Oh, another remark is that for other implicit integrators, like for implicit midpoint and implicit Newmark, you get something very similar to this. Okay. What happens is this y becomes a little bit different. The velocity update to Vn plus 1 gets a little bit different, and you get some funny constant over here, but the idea is exactly the same. You're just minimizing almost the same function. All right, any questions? And it seems the recording survives, so that's awesome. So